Greetings, programs. Welcome to Stegosaurus Studios. My name is Mike, and me and Dummy here, we're hanging out in the shop, at least for right now, while we do this introduction. So in the last episode, I talked about that I was going to do a little math episode, talk about Ackermann steering geometry. So that's what we're going to do. I won't actually make you go through all the math, but anyway, let's go inside the house in front of the computer and let's do that. Okay guys, here we are in front of the computer, and so the good news is I actually figured out how to do the screen capture, screen recording thing. Somebody in the local group told me how to do it. So yeah, let's get into it. So first thing is, so I've talked about this Ackermann steering geometry thing. It's actually named after a gentleman named Rudolf Ackermann. Turns out he wasn't the inventor of it, though. The inventor is a gentleman named Georg Lankensperger. Ackermann was Lankensperger's agent, aka his lawyer. So it's the lawyer's name that gets attached to it, not the actual inventor. So go figure. But basically, Ackermann geometry is this. For any turn, you want the axles extended out from the wheels to revolve around a common center point. So, which is what this diagram shows here. So this is like for your standard car, right? If you're moving upward or moving forward, your front wheels in a turn, the inner wheel turns more than the outer wheel in order to maintain that common center point. If you don't have that common center point, for example, if both of these wheels, turn the same amount, the one wheel would have to it's called scrub through the corner, because it's the outer wheel is moving further than the inner wheel. So it was Lankensperger and then Ackermann that put it in for the patent, that came up with this steering arm geometry to make sure that this happened. So anyway, that is Ackermann geometry. And we want to hold to that when we are steering our speeder. So I'll get into the theory a little bit, but for right now, let's actually look in Fusion at the actual construction as it's designed right now. So we've got our wheel assembly here, or drive wheel. This is the steering arm. So you'll note that the steering arm does not come off at an angle. That angle, called the Ackermann steering angle, is necessary. The steering arms have to come off at an angle when you have both wheels connected together. But since I am separating the wheel steering systems into two separate systems, it's actually a lot simpler geometry just to make the steering arm come straight off of the wheel. So the kingpin is right here. This is the steering arm. This is a ball joint, a tie rod, an inline ball joint, and then this whole assembly here is the rack. The ball joints are in there because the shock absorber, the wheel goes up and down, and so the ball joints will allow the steering arm and tie rod to flex and not bind up. Excuse me. And then, like I said, this is, we've got our rack here. You can actually see the rack. It is mounted to a couple of sliders. They're called linear bearings. Move down a little bit, and they will slide back and forth on this piece of aluminum extrusion right here. And then we've got our pinion, so rack, pinion, and then the motor. This plate right here, I just needed something this is not the final mounting for the motor, but I needed something to, what's called grounding in Fusion. I needed to ground this motor so that I would get proper motion on the pinion. So if we just grab our rack and move it back and forth, you can see the pinion is rotating. And then if we scroll out a little bit, you can see that the drive motor moves in corresponding to the motion of the rack. So from a fusion perspective, everything looks good. And hopefully when I actually get to constructing it, it will work well. So as soon as I finish the motor mount, I will copy the steering system over to the right side. Just so you can see I've got all the shock absorber and the drive wheel copied over. I just don't have the steering system. So I'm just waiting for to finalize this mount here. Okay, so let's go back out here and talk. So this is just a simplified version. So here's our front wheel and here's our two back wheels. So again, we want to adhere to Ackermann geometry. So in a turn, so if we are, front wheel is turned to the right, so we're making a right turn. The back wheel turns and both back wheels turn and the axles meet up at this common center point. So this is how I envision the control to actually work. The front wheel is just going to be a straight linear for on the stick, right? So if the stick is centered, the wheel is at 0 degrees. And if you move the stick all the way to the right, the front wheel will move to 45. So that's my limit. I'm going to range it from 0 to 45 degrees. And again, it'll just be a straight linear function based on stick position. Excuse me. I'm going to do the same on the inner back wheel. So the inner wheel, as you're turning the corner, it's going to do the exact number of degrees as the front wheel, just in the opposite direction. So that's how I'm planning it for right now. This will all be subject to testing once it gets built and goes out there. So linear function here, duplicate this opposite direction. The challenge then is, what is this steering angle for this wheel, for the outer wheel? It's not, so this is shown in this drawing. This is 45 degrees. This is 45 degrees. This is something less, maybe 20 degrees, in order to maintain this Ackermann geometry. So I had to do a lot of calculations. I'm not actually going to take you through all of the calculations because it took me, you're not interested in that. But if we go back to this thing right here, come on. Okay, so here's our drawing now with the thetas, the angles, and different dimensions shown in there. So this was the basis for deriving a whole bunch of equations and doing the solving. So anyway, here's the final equation. So given a steering angle on the interior, that's theta I, that's the inside wheel, you can then calculate the angle on the outside wheel, and this is this big equation right here. So that was all derived just from the geometry in this this drawing that I showed you here. And then to test it, I actually just threw that equation into Excel and just generated a list of, for this angle it converts to this sorts of degrees. So remember in the drawing we had 45 degrees, and I mentioned that it maybe looked like it was about 20. So this feels right. This list of corresponding for these angles. So I think I've got the equation correct. Again, once we actually get out and do some testing with the fabricated thing, we won't know that for certain. So again, to go back to this screenshot, push the stick to the right, the wheel moves the same linear proportion to the right. The inside wheel does the same, but in the opposite direction. We'll use that big ass equation, cotangent, whatever, to calculate the angle for this wheel. So we now know the positions, the desired angles for basically for all three of these wheels. The second half of what needs to be calculated though is the rack travel. So the front wheel is going to be easy because it'll just be gears basically. So we'll just calculate 45 degrees will be a quarter of, or whatever. Yeah, quarter of a turn. No, eighth of a turn, whatever it is. 45 degrees of turn. That'll be easy. The inside wheel will also be easy. Well, the rear wheels, because they're driven by rack, you need to understand how much rack travel corresponds to a certain angle, right? So this rack, when it moves, it pulls. In this case, it pulls the wheel over, and if you move it the other way, it pushes the wheel over. And if I move to the top, we can see the angles of this tie rod changes over the course of the movement, right? So this is not a linear, it's not a completely linear equation between rack travel and the degree that the drive wheel turns. It's something different. So I needed to calculate, how much rack travel corresponds to, let's say, 45 degrees that direction, or 45 or 30 or whatever. So I must have had 15 pages of diagrams and calculations, and I could, for the life of me, I could not relate the rack travel distance to this desired steering angle, right? So we've got this desired steering angle. One is just matches the front wheel, one is calculated from that big long equation, and I just couldn't get it to work. So I brute forced it. So within Fusion, you can, for any joint, you can put limits. So what I did is I put a limit on the travel of the wheel, basically the kingpin joint, and I started actually at 45, so I limited the wheel travel to 45 degrees, and then I measured the amount of rack travel. There's a column that's hidden here, but basically 45 degrees in this, so this is for the right turn, equates to 2.549 inches of rack travel. And then I would go back and restrict the wheel from 45 down to 44 and measure rack travel. And I did that for essentially 45 data points that correspond to from angles of 1 degree all the way to 45 degree. I plotted them in Excel, and that's what we're looking at here is Excel. And then I did a curve fit. So you can probably see here, this is not a straight line, so it is not linear. In this case, the best curve fit is actually a second order polynomial. It's a little less complicated for the left turn. It's a third order polynomial. This is second order polynomial. So I now have this equation here that shows the rack travel, which in this case is y, based on the degrees, which is x. So I can use these two equations to then calculate the amount of rack travel. So that's basically how the steering system works. You push the stick, it tells the front wheel and the inside wheel where to go based on linear. It calculates the outer wheel angle, and then the two angles for the rear wheels are calculated with these two equations, and that will equate to rack travel. And then with the rack travel, you can then calculate how many turns, or what portion of a turn of the pinion, right? So we've got our little pinion here. And so based on, let's say, that amount of rack travel, how many revolutions or part of a revolution does the pinion make, and then that will then tell you how much signal to send the motor, or for how long to turn the motor, to make the pinion do that amount of travel. So that is how it's planned to work. And once it's all built and it's all got all the power hooked up to it and it's automated, we will see. I suspect there might be some tweaking and things to make because there's things like lash, backlash, there's just putting it together. I don't know how exact I can be on putting it together. So hopefully when it's all said and done, it will work. And so yeah, that's that. All right, we're back out here in the shop. Hopefully that was instructional as far as how the steering stuff is going to work. I'm really anxious to actually get it finished and get an order in for all that material and get it put together so that we can actually see how it all works. So that's it for this episode. Hopefully by the next episode, we'll actually have the front steering figured out and that order that I just mentioned placed, and we'll start building stuff. So until next time, see you later. Thanks.